All right, with some of these fundamentals under our belt, let's move on. In the last set of slides, we talked about expected value, we talked about variance. Now I really want to move to expected utility to give us a theory that will predict how people would choose among different risky prospects. So what are we trying to do here? Well, we want to introduce a theory to describe choices among uncertain outcomes. What we want is a way to characterize how highly a person rates an uncertain situation. How much, quote, utility do they attach to this uncertain situation? And we're going to do it all in terms of a new utility function, U of W. W, just think about that as a summary of all of our resources. You could just call it wealth. And so where we're going with this, and I'll talk about this utility function in a second, but where we're going with this is a theory that yields a choice, for example, between the more and less risky job, among other things. What about this utility of wealth function, U of W? So what are we talking about here? Well, this is a function that shows how utility varies with W, wealth. So think about a diagram with wealth on this axis. More wealth is this direction, so this is W. On this axis, we measure how highly the person rates the situation, the utility of wealth. So for example, for a particular level of wealth, W0, just go up to the function and then go over, and bingo, there's the utility of W. Now I should note, the way I've drawn this picture right now is I've drawn this picture in a particular way, this function. So more wealth has higher utility. This thing slopes upward, but the rate at which it slopes upward declines. So I've drawn it this way. We'll talk a little later in the video about consequences of alternative assumptions, like it could look like this, or it could even look like this, but this is the most natural one, and you'll see why shortly, and that's the one we'll tend to work with. But we will, as I say, we will talk about what it would mean for these functions to have these other shapes. All right, so we're about ready to hit the specifics of expected utility, so let's do that. What we're supposing is that attitudes toward risk can be described by a utility function over wealth. And so what this new thing is, this expected utility thing is, now you can guess it's related to expected value. Expected value was probability weighted sums of the wealth outcomes. Here, this is going to be probability weighted sum of the utilities of the various outcomes. So not the wealth themselves, but rather the utilities of them. So let's just state it in a sort of a general way, but you'll see lots of examples real shortly. Here we have these different things that could happen. State 1, state 2. So these are states of nature, different things that could happen. And so let's say in state 1, what you have is W1. In state 2, what you have is W2. So these are amounts of wealth, and they're different. The probability that state 1 occurs is P1. Now these states, state 1 and 2, are the only two things that can happen. So the probability that state 2 occurs is P2, and it's 1 minus P1, because again, these are the only two things that can happen. So their probabilities have to sum to 1. Finally, this last column shows how well off the individual is in each of these two states. And again, how well off is being measured by the utility of wealth, not the wealth itself. In state 1, the individual's well-being is measured by U of W1. In state 2, the individual's well-being is being measured by U of W2. So this expected utility thing, which is going to be really key for us, is this, well, literally the probability weighted sums of the utilities of the outcomes, but it's P1 times the utility of W1 plus 1 minus P1 times the utility of W2. That's the expected utility. Now, what are we talking about? A picture really helps, so let's talk about this picture. There's a lot in this picture, so we'll go slowly. So what we have on this axis, again, is wealth, and on this axis, the utility of wealth, so how well off. So think about how high we are up in this direction, is a measure of how well off we are, how much we like some situation. For example, suppose the individual had W1 with certainty. So there's no expected stuff going on here, just with certainty the individual has W1. How well off would he or she be? Well, go up to here and then over to here. This individual would be this well off. That's how high on this vertical axis. You know, by contrast, if the individual had more, they had W2, how well off would they be? Well, you could trace it up to the curve itself and then over to here. That's how well off they would be. But now suppose instead of having either of those two amounts with certainty, let's say the individual instead faces some possibility of having W1 and some possibility of having W2. Well, two questions we could ask. One question we could ask is, what's the expected value of what they have? And that we could look at right here. Now, this is sort of drawn for, about P1 equals 0.5, so this is halfway between W1 and W2. The expected value then would be halfway between these two. But now what we're asking, the thing we're really asking is about the expected utility. So how well off are they facing the prospect of, maybe having this, excuse me, and maybe having this? Well, the key idea is that expected utility is measured by this, the probability weighted sums of this and this. And what the expected utility is, it lives on the straight line that connects this dot with this dot. Indeed, it's this sort of darker red straight line between here and here. And so if we're going halfway over, then what we find is expected utility is here. Let's just trace this over. So there's the expected utility. Now, just to make it really clear what that is, let's contrast that with a very different possibility. Suppose instead of facing the possibility of having W1 with P1 and W2 with P2, suppose instead the person with certainty had this amount, this expected value amount. How well off would they be then? Well, for that we go straight up to here and over to here, and there it is. And what do we see? We see that the utility of having this expected value is greater than the expected utility of maybe having less, maybe having more. Now that kind of makes sense. That tells you this person doesn't like risk. This person would rather have, and it's sort of take it back to those examples, like this person would rather have 1,000 with certainty than maybe having 900, maybe having 1,100, where even the maybes are 50-50, so the expected value is 1,000. The person would rather have 1,000 with certainty. So that is exactly what this picture means. And I should say that's what happens when the curve curves over in this manner. All right, let's continue. In fact, let's evaluate the jobs examples in terms of this theory. So in order to do this, we need to say exactly what the utility function is. And so let's use the utility function u of w equals square root, that's kind of a funny square root symbol we get there, square root of w, and it's another way to say that it's w to the 0.5. Now, that is a function that looks like this. It's upward sloping, but it curves over. And what we would say, since that person is not going to like risk, we call that a risk-averse function. So this is an individual who is risk-averse with, in particular, the function u of w equals square root of w, or w to the 0.5. Those are just two different ways of saying the same thing. All right, well, refreshing our memory about what those jobs examples were, job 1 had a 0.5 probability of paying 500 and a 0.5 probability of paying 1,500. Job 2 had a 0.5 probability of paying 900 and a 0.5 probability of paying 1,100. So how do we think about those in these diagrams? Well, here's the answer. So here's job number 1. Here's 1,000. Here's 500. Here's 1,500. Now, the 50-50 situation has an expected value equal to 1,000. But of course, we don't have 1,000 with certainty. Instead, what do we have? What we have is the expected utility that's 0.5 times the utility of this plus 0.5 times the utility of this. It's along this straight line, halfway between. In mathematical terms, let's go over to the purple box over here. It's the purple outline anyways. what we're doing is we're calculating that expected utility. It equals 0 0.5 times the utility of 500 plus 0 0.5 times the utility of 1500. That's 0 0.5 times square root of 500, which is 22.361, plus 0 0.5 times the square root of 1500, which is 38.730. Add it up and use a calculator, it equals 30.546. So what we're saying is 30.546 is how high up we are, this sort of how happy dimension, and there it is, the expected utility. Contrast that with having 1,000 with certainty. Having 1,000 with certainty, well, that delivers u of 1,000, which equals square root of 1,000, which is right here. It's 31.62. And notice that it's bigger than 30.546. Okay, there's one more point that I want to make on this slide, and let's look down at this lower corner and ask, what amount of money is the job worth? So again, you have this job, and with 0.5 probability it pays you 500, with 0.5 probability it pays you 1,500, and so what's it worth to you? Well, it's worth in utility terms 30.546. What I'm asking here now is, what amount of money with certainty would make you as happy as facing this risk? So this is the how happy associated with facing the risk, but there's also some amount of money which with certainty would leave you as happy as facing that risk. And so let's just go across here and hit the line. Let's go straight down. So what is that line? That's just the line that says the utility of particular amounts of wealth. Let's go straight down and say, what amount of wealth with certainty would make me as happy as facing the risk? And there it is, 933. Or if we want to split hairs, it's 933.02. How do I know that? Well, there's the utility level, and it equals the square root of W. So if I square both sides, I get 933. So summing up, what we're saying here is that, facing a prospect of 50% of the time getting 500 and 50% of the time getting 1,500, if I had the utility function u equals square root of W, which means I don't like risk, then I'd be equally happy having 933 as I would facing that risk. Now this all kind of makes sense, because if I don't like risk, I'd rather have something that is, I'd be as happy even with something that has lower expected value. Remember, the expected value was 1,000, but 933 with certainty would make me as well off as facing the risk. Let's compare this with job 2. Now, even before we do any calculation, let's think about how this is going to play out. Job 2 has the same expected value as job 1, but it has less risk, because it's only got these two possibilities, 900 and 1,100. So, do we think the expected utility would be higher or lower here? Well, it certainly ought to be higher, because the individual's not facing as much risk. Okay? So, here's the calculation we already did for job 1, and its probability weighted utilities of 500 and 1,500. Here we'll do it again for job 2, where the two wealth possibilities are 900 and 1,100, so the utility possibilities are u of 900 and u of 1,100. When we calculate this one out, we get expected utility of 31.58 and so forth, which is bigger, not surprisingly, I think, than the expected utility of job 1, which was more risky. So, job 2 has higher expected utility. It has the same expected value, but higher expected utility. And that's, of course, related to the fact that it had less risk. Right, let's try a different kind of example that this same theory can illuminate. So let's think about literally an insurance example. And so let's think about a fire. Let's hope it's a fire that only destroys wealth and doesn't hurt anyone. So we can summarize the states of the world in terms of the wealth that the individual has. So the individual has a decision. Should he or she have insurance or no insurance? So here's the no insurance line. Here's the insurance line. Over here we have states of the world. Usually there's no fire. So 99% of the time there's no fire. 1% of the time there's a fire. Now if you have no insurance and there's no fire, let's say you have 100. So that could be 100,000, whatever you like. But let's just say it's 100. If there is a fire, your property is destroyed, and so your wealth falls from 100 to 50. So that's all in the context of not having insurance. So, you could say that's like going naked without insurance. Either you have 100 with probability 0.99 or 50 with probability 0.01. Now, on the other hand, you could have insurance, and let's be clear, this is full insurance. So this means no matter what happens, you have 100 minus the premium. So the premium is the amount you pay for insurance. Over here, what that means is you have 100, and then you lose 50 because there's a fire. But it's full insurance, so you get a check for 50, but of course you still have paid your premium. So that ends up being 100 minus premium. The point being, though, with full insurance, you have the same wealth in both states of the world. All right, let's think about working the problem. So again, let's suppose the utility of wealth is described by square root of W, which is the same as W to the 0.5. And that shape, again, is a risk-averting shape. That's a person who does not like risk. The questions I want us to think about are the following. What are the expected utility and certainty equivalent of the uninsured states? And again, the certainty equivalent, we talked about it on the last slide, but that's the amount of money with certainty that's equivalent in utility terms to being in the uninsured state. And that's going to be a helpful number for telling us how much the person would be willing to pay for insurance. All right, here's a picture, not entirely drawn to scale, just so that we can actually see everything. So let's summarize what's going on here. Here's the wealth if there's no fire. Here's the wealth if there's a fire. So this is 50, this is 100. Now the idea is that the expected utility is 99% of the way between here and here. I say it's not quite drawn to scale, and it's not. But 99, so let's talk about two things. What is 99% of the way between 50 and 100 along the W-axis? And that's 99.5. Why is that? Because 50 plus 0.99 times 50 equals 50 plus 49.50, or 99.5. So what is that? That's the expected value of the individual's wealth if the individual is uninsured. What about the expected utility of being uninsured? Well, that is 0.99 times the utility of 100, so it's 0.9 times this quantity, plus 0.01 times this quantity. So what we're doing is moving 1% of the way from along this line, from here to here. So there we are. And now the how happy dimension is this dimension. How happy am I? It's right here, the expected utility. So if we calculate that out, the 0.99 times utility of 100 plus 0.01 times utility of 50 equals 9.971. So there we are. That's 9.971. Now, those numbers by themselves don't mean all that much, but we can also ask what amount of wealth, so for what W is U of W equal to 9.971? Now, what are we asking when we ask that question? We're asking what amount of money with certainty would make me as happy as facing the risk of fire without insurance. So if I solve that, I'll be finding the certainty equivalent. And indeed, so it's square root of W equals this 9.971. If I square both sides, I end up with W equals 9.971 squared, which is right down here, 99.415. All right, so that's a number that kind of has some meaning for us. That's the amount of wealth with certainty that would leave me as happy as facing the risk. And indeed, it's right here. So we take this how happy over to the curve and then drop straight down, and there it is. So let's think about the benefit of insurance and what this has to do with insurance. This person that we're describing would be as happy with 99.415, $99.41.5 with certainty as with being uninsured. So how much would this person be willing to pay for insurance? Well, they'd be willing to pay up to 58.5 cents. If insurance were less than 58.5 cents, full insurance, then they'd be better off with the insurance than not having the insurance. If insurance were 58.5 cents, they'd be equally well off buying the insurance and just facing the risk on their own. Now, what's really interesting here is that this 58.5 cents, which is how much they're willing to pay for insurance, is actually bigger than what it costs to write the policy. Now, what do I mean by that? Well, what's the expected payout on this policy? Well, this insurance, pays out $50 1% of the time. So there's a fire 1% of the time, and when there's a fire, it pays out $50. 1% of 50 is 50 cents, a half a dollar. 58.5 cents is what the individual is willing to pay for this insurance, but the actual expected value of the insurance is only 50 cents. So what that means is it's possible for an insurance policy that's priced somewhere between 50 and 58 cents to actually make the this person who faces risk better off. Now, there is just a little bit of an interesting aside to mention. Why would we think of the insurance firm as being risk neutral here, or why would we only think about the expected cost of the policy? And the reason there is the insurance company has lots of wealth. They're able to diversify across many possible fires, so it's actually not very risky for them. So really just thinking about the expected cost is really a relevant idea, whereas the individual has much of his or her wealth at stake in the possible fire. So this is not a crazy way to think about this problem, but the punchline here, I want to make sure we don't miss that. The punchline is the individual, because he or she does not like risk, is willing to pay more for this insurance than it costs to write it. And so it's possible for insurance to make this individual better off. All right. I said I'd come back to this question about shapes of these utility functions and what they mean. And so just a little bit of notational reminder here. If we have U of W, this thing we call U prime, that's the delta U with a change in W, delta W. And so this U prime positive just means when W goes up, U goes up. And that just makes sense. More wealth leads to more satisfaction in this sense. But this U double prime, this means that the rate at which wealth goes up declines. So this is associated with this kind of a shape, W and U. U double prime equals 0. Now that just means a straight line, W here and U. And finally, somebody who loves risk looks like this. We call it U double prime positive. This is just notation from the idea about what's happening to the change in utility as we change wealth. And the idea is that this declining, maybe a much better way to say it is to say this one here is declining marginal utility of W. This one here is constant MU of W. And this one here is increasing marginal utility of W. Now the point I wanted to make on this slide is think about putting a gamble into a slide for a person with risk-loving preferences. And so let's say maybe they're going to have this and maybe they're going to have this with some probability. The expected utility line for such a person is like that. And what's interesting is it's actually above the utility curve itself. So this person loves risk. Okay? That's why we call such a person risk-loving. That's sort of pathological. I mean, most people don't like risk when it comes to things like the possibility of their house burning down. There is, of course, some love of risk in gambling, but that's a kind of a different sort of leisure activity. All right. What do we take away from all this? Well, a couple things. First of all, expected utility is the probability-weighted sum of the utilities of the outcomes, not the wealth, but the utilities. And it can be used to describe preferences over uncertain outcomes. So what's neat is we've introduced an actual theory that gives predictions about how people would choose between different risky opportunities or between, say, a risky thing and a certain thing. A second point I'd make is that most people are risk averse. More is better is a usual characterization of wealth, but typically people have declining marginal utility of wealth, so functions like U equals W to the 0.5 are reasonable ways to model risky attitudes towards risk. And finally, dislike of risk explains the demand for and the benefit of insurance.